So maybe you did these last two Hess's Law problems just for fun, and you want to check and make sure you got them right. So if you needed a little extra practice, or again, you're just double checking, triple checking, make sure that you're a master of Hess's Law, let's attack this combustion of ethine. Okay, so I want ethine on the reactant side. And I see that in the third elementary step, it's on the product side. I could work with that. What if we take step 3 and flip it? Do you think these are kind of fun almost? Isn't this like a total change from equilibrium and K values and ice tables? I think they're kind of fun. And I do love ice tables as well, but it's just a little refreshing break. So we're going to flip that third step so that we get the ethine, C2H2, producing 2 carbon and the hydrogen. And then we'll kind of plot our delta H values in units of kilojoules. Okay, let's see here. So I'm going to take that last step and just flip it. So we'll say negative 230 units of kilojoules. Okay, I like that. Oh. Okay, so what do you do with this weird 5/2 oxygen thing? Often we balance equations with whole number ratios, but you can have decimals or fractions. If we think about it as a ratio of moles, you can have like a part of a mole. Well, if we think of it as molecules, you can't have like half a oxygen molecule. Well, we could have half a mole of oxygen. So it is okay to see these half ratios or partial ratios in the balanced equation. And again, often with a combustion, they'll do this so that what you're calculating is the combustion per 1 mole of ethine. They might call this like the molar enthalpy of combustion, which just means what is the energy change for the combustion of 1 mole. Okay, so that oxygen is kind of funky, and I'm not quite sure what I want to do with that, because I do see oxygen in both of those other elementary steps. So I don't know, let's just skip it for now. I promise, again, these are always going to work. So what if we move on to the carbon dioxide? I only see carbon dioxide in one of the elementary steps, so let's go with that. Let's try taking maybe this first step. I want 2 carbon dioxides. Let's try multiplying this guy times 2. Okay, so I will have then 2 carbons and 2 oxygens, O2, forming 2 carbon dioxides. We're going to take that negative 390 times 2, or negative 780. It does not matter what order you write these elementary steps. That does not matter at all. In the end, when we want the total energy change, we're just going to add it up. So it's okay that I skipped the oxygen and I moved on to another component of the reaction. Okay, so let's do a little assessment here. What do we got? What do we want? I want you. Ew. Oh, well, this is kind of cool. Right away, we could get rid of these 2 carbons. I produce 2 carbons. I consume 2 carbons. I don't like that. I do not want that hydrogen, so I'm hoping we can get rid of that. When we take care of the water, we still don't have water on the product side, and I know I need a little more oxygen. We'll deal with that. Oh, perfect. Hey, look at that second step. It forms 1 mole of water. That's exactly what I want. So let's use that second step straight up. The hydrogen plus the half mole of oxygen forming 1 mole of water. And then we'll use this delta H as negative 290. Watch what happens. Okay, so I got the water. I wanted that. I can get rid of this hydrogen. I produce hydrogen. I consume hydrogen. And check out the oxygen. It always works out, doesn't it? I have 2 oxygen and a half oxygen. Well, what do you know? That's equivalent to 5 halves oxygen. This would be like 4 halves oxygen plus 1 half. That is my 5 halves oxygen. It works. Perfect. So if I got the overall desired reaction, which I think I do now, I have the ethine, H2, the 5 halves oxygen, I have the 2 carbon dioxide, I want you, and I have the water. All we got to do is add those delta H values. This is exothermic. Interesting. Let's say like negative 1,300 kilojoules. Does that make sense? Absolutely! Last time I checked, when something is combusting, it means it's burning. Combustions are always exothermic. So yeah, that makes sense. We're releasing 1,300 kilojoules per mole of ethine combusted or burned. Okay, I like that. That makes sense. Let's try one more. Make sure we got this down. And if you feel like you are a master of Hess's Law and you want to move on and try some in the homework, go crazy. Go nuts. Can they ever make Hess's Law any more difficult? Not really. I mean, they could add more elementary steps. I mean, it might look a little more daunting, but we just kind of attack them and solve them all the same way. We have some diborane. Diborane is not boring. Ha ha. It's actually a fuel. It's highly flammable. It's a rocket fuel used in the U.S. space program. Interesting. Calculate the enthalpy change for the synthesis of diborane. Okay. From its elements, boron and hydrogen. So again, let's just see what we can do to get 2 boron on the reactant side. How about step 1, huh? It's perfect. So let's start with this bad boy. The 2 boron. Weird. The 3 halves oxygen. I'm hoping to get rid of that at some point. Producing, B2O3. That is not what I want. Diborane should be B2H6. I'm hoping this is just an intermediate. Okay, so delta H. These are in units of kilojoules. We're using that straight up. Negative 1,273. Okay, so I have the boron. Let's just move on. Let's see if we can get the 3 hydrogen. 3 hydrogen. Well, the only place that I see hydrogen is maybe this guy, the second step. I want 3 of them. So let's say we take this, I guess the third step listed here. This third step and multiply by 3. So everybody gets multiplied by 3. I'm going to have 3 hydrogen. Ooh, interesting. I have some oxygen. 3 halves oxygen. And then I'm going to produce 3 waters. And did you notice that I'm not using a lot of phase symbols? I'm not using any phase symbols, which is fine. I mean, my final answer is the delta H value. And this is enough of showing your work. I'm showing the equations that I used and how I manipulated them. I add up the delta H's and boom, I'm done. However, here's what kind of tricks people on this one. This is water liquid. Here in this last step is water in the gas phase. Because there's water in 2 different phases, I am going to put that this is water liquid. Just to remind myself that that's water in the liquid phase. There is a different delta H value depending on if you form water in the liquid phase or water in the gas phase. If the water is in the gas phase, There must have been more energy produced. Okay, so I am going to make note that that's liquid, and I'm going to multiply negative 286 times 3. And I'm going to say negative 858. Okay, cool. So I have the two reactants that I want. Awesome. I've got a bunch of other random stuff in there that I do not want, but let's just keep plugging along. Let's try to produce the two, one, borane, the B2H6. B2H6, I see that in one spot, in the second elementary step. There she is. It's listed on the reactant side. I want it on the product side. So let's take this bad boy and flip it. I only want one B2H6, so I don't need to multiply it by anything. Let's flip this sucker. So we have, I like this, B2O3 plus 3 waters. I'm going to just make note that this is water now in the gas phase. And then I'm going to have the B2H6 and the 3 oxygens, O2. Okay, so all I have to do is flip the sign of the delta H. So we'll make that positive 2035. All right, so let's do a little inventory. Let's see what we got, what we don't want. I think I have the reactants. Yep. The boron, the 3 hydrogen, excellent. I have the product. I have the 1 borane. I'm hoping the rest of this garbage will cancel, right? Well, this guy does. Here's an intermediate. B2O3 is formed. B2O3 is produced. You are gone. Check out what happens with these oxygens. On the reactant side, I have a total of 6 halves oxygen. 6 halves oxygen? Is that equivalent to 3 oxygen? Bingo! Here's 3 oxygen produced. We can cancel those 6 halves oxygen on the reactant side. I told you these always work, right? Now, before you get too excited, there is 3 water produced and 3 water consumed. They're not the same phase. Well, that's why they give you that last step. They give you that conversion between water liquid, water gas. And it makes sense that it's endothermic. I have to add 44 kilojoules to vaporize 1 mole of water, the heat of vaporization. Okay, so we need to use that. What do we got here? We don't want any of these waters, but in order to get the 3 liquid waters to cancel, I need 3 liquid waters on the reactant side. And then on the product side, I want to get rid of these 3 water vapors. So I need to take this third step and just multiply her by 3. So I'm going to go 44 times 3. We can leave it positive or endothermic for 132. Does that kind of make sense? We had to make sure that the phases were right. So now I have 3 liquid water, 3 liquid water, 3 gaseous water, 3 gaseous water. I think we're in good shape here. Do we have the balanced equation? I think we do. We have the 2 boron. We have the 3 hydrogen. And then on the product side, yep, everything's crossed out but the B2H6, and that's the only one I want. So just keep an eye out for something like that water where it's in different phases. It's usually something that people will overlook if they got the answer wrong. And they'll be like, I plugged this in my calculator a million times and I'm not getting the right answer. Oh, dang, I didn't notice that the water was in a different phase. Okay, so we add these all up. And delta H is endothermic. endothermic. 36 kilojoules. Now this is 36 kilojoules for the production of this diborane. Obviously, if it's a rocket fuel, then when you burn this diborane, it would be exothermic. But the production is slightly endothermic. There, everything you need to know about Hess's law. You are officially Hess's law masters.